To run the case in parallel, we first decompose our case using the decomposePar utility. After the case is decomposed, run the simulation in parallel and then reconstruct the case for the post processing in ParaView. Okay, so let's start by doing a live simulation. Okay, so I'll be using again the cavity case to run the simulation in parallel. Okay, so first for using that cavity case, we have to go inside the foam tutorials. Then I will go inside incompressible. Then I will go inside ICO foam. Then I will go inside cavity, and here is another cavity directory. I will go inside that, and this is our case. Okay, so we will go back one step and we will copy this cavity directory to our home directory. All right, so yes, it is my cavity. All right, I will clear the terminal. Okay, so we will open the cavity. Okay, so we will go inside system. Okay, so now block mesh dict. First we will go inside block mesh dict, because in the simulation, previous simulation, what we have done. Okay, so let me run first the block mesh. Okay, then I will show you what changes I am going to make this case for usable for for parallel processing, because generally, because right now we ran it previously and it ran perfectly without any parallel processing. Okay, so first we will make it to run it feasibly for the parallel processing. Okay, so first run block mesh. Okay, mesh has been complete. We will go and we will make the .foam file, then we will open it with the help of foam.foam, paravi.exe foam.foam. Okay, so it will take some seconds to open, or your system is much faster, then it will open very fast in your system. So it depends on the system speed. Okay, so it is here. So I'll press apply, and yes, so for to view the mesh, I'll press wireframe. So you can see that right now the mesh is very coarse. Okay, so what I will do, I will increase the number of points here, means I will make the mesh finer. Okay, so that the number of cells will increase, so that it will become feasible to run, to use the multi-cores for running the parallel processing. Okay, because if it is not feasible, why to use the other resources? Okay, because it will ultimately use the power. Okay, so why to waste the energy? Okay, so I will close it, and then okay, so let us first make the mesh finer. Okay, so for that we have to go inside the system, then we have to go inside block mesh dict. Okay, and then here, okay, we can make the mesh finer by changing the nx and ny. Okay, so what we will do, we will just increase the number of blocks. Okay, so here currently it is 2020, let's increase it to 50 and 50, press ok, and all right. So what I have done to save this, save anything you are editing in nano editor, how to save it. So again I will just make the changes. Again I will put 0. Okay, to save it, press Ctrl O. It will ask for the file name to write, you have to keep it same, press enter. Then to exit, press Ctrl X. Okay, now you have exit. All right, okay, we have done it. All right, so if we'll go to check mesh, to check the mesh, currently the number of points are okay. Okay, it has made the changes, I think. Let me clear the terminal first. Clear, go back, system, nano, block mesh dict. Okay, initially it was 20 and 20. Okay, and then I will go back again, run the block mesh. Okay, then I will again run check mesh. So initially it was, the number of points was 882. Okay, now we will change it. So we will change it. We will go inside the system, press and go to nano block mesh dict. Okay, change the number of blocks to 50. Control O, Control X, go back, then again run the block mesh. Okay, then to, okay, now it has changed to 5202. So the mesh has become finer. Okay, let's check it in the paraview also, paraview.exe foam.foam. Okay, that physically also you can watch that. Okay, the mesh has become finer. I will apply, choose wireframe, and yes, you can see that the mesh has become finer. All right, we will close it. Okay, now to run it parallelly, we have to make the changes in the another dict. Okay, that is decomposeParDict, which is inside the system. Okay, so like for the block mesh dict is there. For controlling the simulation, control dict is there. So for the parallel simulation, that is decomposeParDict is there. So we have to make some changes here also. Like first you have to run parallelly, so it must be there. Okay, and set up according to your processor available or number of processor you're going to use. So I'm going to use number of processor 4. So I have to change this to number of subdomains to 4. All right, then method hierarchical, let's keep it like this. There are two other methods also, which is simple and scotch. Okay, so let us use method hierarchical only, and then in the coefficients also we have to make the changes accordingly. So we will change it to 2, 2 and 1. Okay, press Ctrl X to exit, then to run it parallelly, to divide the case into different processors, we have to run this command decomposePar, press enter. Now our case has been divided to 4 different processors. This processor will solve some region of the case, this processor will solve some region of the case, and so on. Okay, again we will clear the terminal. Now to run the simulation. Okay, now what we have to do, to run the simulation. Okay, we cannot, like, when we ran it on a single processor, what we have done, we have simply typed the name of the solver and press enter. Okay, but to run it parallelly, we cannot do it like that. So we have to run like that, mpi run minus np 4. 4 is the number of cores which you are going to use. So it will be same as we have mentioned in decomposeParDict. Okay, so we have mentioned 4, so we are mentioning 4 here. Then we will write the name of the solver, which is icofoam. Then we will write parallel. Okay, this is the format of running the simulation parallelly, and then press enter. So it is solving the the simulation parallelly, and it is completed. Okay, because it's a simple case, so that is why it is. So my aim for this lesson was like to show you like how to perform the parallel processing, not to run a complex complex simulation. All right, so that was my point. Okay, this much of simulation can be run on like simply like single processor, which we have run also beforehand, but my aim was to show you like how you can perform, what steps you have to perform to run a simulation parallelly. Okay, so these are the steps common. If there is any complex also, you have to perform the same steps to run it parallelly. All right, that is the part. So now let's go, let's post visualize our results. Okay, so yeah, so first we want to reconstruct it. Okay, so if you will go inside any processor, you will find that the time steps have been written. Okay, so we want to, and these time steps will be there in each and every processor. Okay, let me show you. So if we'll just see to processor 1, you can see the same time step. If you will just see processor 2, same time step, 3, same time step. Okay, only okay, yeah. So these are there. Okay, so but in these time steps contains the different parts of the domain. Okay, so we wanted to club it and write it outside. So for that, reconstruct part will be used. So you have to do it like that: reconstruct par minus time 0 to 0.5. Okay, this we wanted to write. So this means 0 to 0.5. This line means only this part means 0 to 0.5. Okay, and press enter. Okay, if you just press ls and press enter, you will find that all the time steps have been written. It has clubbed all the results, all the solving of the different regions, club it single and return it all together outside. Okay, again I will clear the terminal and then I will go to paraview to visualize our result. Okay, press apply and yes. Okay, so if you'll go to velocity, okay, you can find that it has done some changes. Some changes have been there. Okay, so that is the part. All right, that is the part that I wanted to show you. That I wanted to show you here. Okay, like how to make the decompose par. Okay, all right. So like this, you run the simulation. Okay, so you have successfully run an OpenFOAM case in parallel. This is essential for large and complex simulation.